Alright, hello everybody. So today we're talking about strategies for testing series. This is really just an overview of everything that we've learned so far in the chapter. So I'll say if you're given a series and you're asked to find whether it's convergent or divergent, then your easiest tools, so the quickest slash easiest tier of tools is going to be, so number one would be you would see, well, is this a geometric or a p-series? Right, so is this a geometric series or a p-series? So sometimes you can actually get some series that don't quite look like geometric series, but if you somehow do a little bit of algebra, you can get that they're geometric series. So I'll say here that these are sometimes distinguished and requires algebra, right? Because sometimes you have to do a little bit of algebra to actually prove that it's a geometric series. All right, so your second easiest tool to use is going to be the test for divergence. And as the name suggests, it can't tell you if something is convergent. But sometimes if it's divergence, then this test will pick it up, right? So what the test says is if your limit as n goes to infinity either does not exist or is non-zero, then if you're adding together all of these terms, then you're going to be getting something that's going towards infinity if your limit's non-zero, right? So that is going to tell you if that limit is non-zero, that's going to tell you that you've got a divergent series. So that's another very useful and easy tool to use. And our third nice tool to use is going to be the ratio slash root tests. Okay. So our next tier of tests, let's call this the medium tier. Right, so you kind of just go down the list and see what's the easiest test I can use, and is that going to solve my problem for me? So number 4 here is going to say the alternating series test. And here to tell whether your series is alternating, this is if you see either a minus 1 to the power of n or minus 1 to the n, either plus or minus 1, right? So if this is a plus or a minus, it actually means the same thing. So if you see one of these in your series, then that means that you're an alternating series, and this is probably the test that you want to use. And notice for the alternating series test, you need a decreasing sequence whenever you take the absolute value and you get that sequence of b, so bn. So the key here is that you need to take the derivative of bn and solve for bn prime, saying the derivative of bn is less than 0, because if the derivative is less than 0, the rate of change is negative, meaning it's decreasing, to show bn is decreasing. Okay. And the fifth tool that we have to use, so number 5, is going to say the comparison tests. So here we're asking, does the series look like a geometric or P series. Right, so when I say looks like, I'm saying just, well, maybe it looks very close, but instead of maybe say 1 over n squared, you have, let's say, 1 over n squared plus 1. Then that looks very close, but it's not quite the same thing, so we're going to use the comparison test to compare the two series. So the key here is finding the comparison series. Right, that's oftentimes the hardest part there. All right, so for the direct comparison test, I'll say what we want to do here is leave something off of the top or bottom of the original series, and also to remember that sine and cosine are bounded by -1 and +1. Okay, so let's just draw some examples of what this looks like. So, example, let's say we have the sum of 1 over 2 plus 3 to the power of n. And we're saying that we're trying to get this to look like either a geometric or a p-series. Well, notice if we got rid of this plus 2, well, what would actually happen? We'd say, well, if we got rid of this plus 2, we can factor out a third, and then it looks like a third times 1/3 to the n minus 1. So we would actually want to compare it to the sum of 1 over 3 to the n, which, as I said, is actually a geometric series. So you can see here you're just looking at your original series, looking for something to take out and turn it into something that you can actually work with. And similarly, if you had something like the sum of sine x over the square root of n, well, as we said, sine is bounded between -1 and 1, so the biggest value that this is going to take is +1. So we know that this is going to be less than or equal to the sum of 1 over the square root of n. And just because sine x is always less than or equal to 1, and we know that this is actually equal to the sum of 1 over n to the 1/2, and now that's a p-series, where p is equal to 1/2. Okay, so that's how we can use our direct comparison test. And if we were using, let's say, the limit comparison test, because sometimes we're not able to use the direct comparison test, then we only take the dominant meaning the highest degree term from the top, and the bottom. Okay, so let's say we have something like, let's say example, let's say we have something like the sum of the square root of n cubed plus 1 over, let's say we have 3n cubed plus 4n squared plus 2. Right, so this thing looks a little bit complicated. But we said here if we're using the limit comparison test, then the thing we're comparing it to, we just take the dominant terms in the top and the bottom, so the biggest powers of n. And if we do that, then we're going to compare it to, let's say here this is going to be the sum of, inside of the square root we just take the leading term, which is n cubed, and in the bottom here we take the leading term, which is 3n cubed. So we can rewrite this as the sum of, so up here we have n cubed and we're taking the square root of it, so that's the 1/2 power, and you multiply that by the 3, so you're going to get n to the 3/2 power over 3n cubed. And if you're dividing things with the same base and different powers, then you subtract the powers. So 3/2 minus 3, so that's 1.5 minus 3, that would be negative 1.5. So this would be, so here you would get 1/3 times the sum of, this would be n to the negative 3/2, which you can, again, go ahead and rewrite as 1/3 times the sum of 1 over n to the 3/2, and now 1 over n to the 3/2, that's actually a p-series, so you can analyze that. Okay, and we've just got one last type of test that we're able to use that we went over. So if all that doesn't work, then we resort to what I'll say is the hardest here, which is going to be, so number 6, which is the integral test. Okay, so I'll say that this is hard because we need to prove that f is decreasing, continuous, and positive, and on top of all that we need to solve an integral. Right, so that's kind of a lot of work, right? So we've got to prove all of these things, and let's say here the best indicator, so the best indicator that we want to use this test, to use the integral test, is an apparent U substitution. Right, so if we see an easy U sub that we can make, then we can actually go ahead and solve the problem just by using the integral test. So let's say, for example, let's say we have the sum of n times e to the negative n squared. Then here you can see if you were solving this integral, you would just let u equal to the negative n squared, and then a version of its derivative appears right here, since you have n right there. And another example would be, let's say you have the sum of 1 over 2n plus 7 to the power of 3. Let's say that this is the series that you're given. Well, here again, if you did a u substitution where this inside part is u, then the derivative of u is actually a constant. So you don't need to look for u in the other part of the integrand. So this is also a thing that you can definitely integrate, and that's a clue, since you can integrate this using u substitution, that you're actually going to want to use the integral test.